Hello everyone, my name is Carlos, and today I'm going to be talking to you about the concept of 90-degree angles, or as it is technically referred to as something being orthogonal to each other. And in case you don't know, orthogonal just means that, suppose these are vectors v1, and this vector is 2. It means it'll form a 90-degree angle. That's all orthogonal means. And this is a really powerful concept in both physics and math. Because when you have a series of vectors interfering with each other, it can be really confusing and hectic to point out and find every single vector and then add out the resultants. So the way that this 90-degree concept works is that every vector basically has two components. A component that goes in the what is referred to as the x direction, and a component that goes in the y direction. Every single vector in physics works like this. And this is where the 90-degree angle comes from. So these two vectors that are orthogonal to each other make up this resultant vector. And then from here, instead of calculating this vector, this vector, this vector, this vector, and this vector, you can simply take all of these, all the little x's, and add them up. So the summation of all of them, of all of the x's, will give you what's called the resultant vector in the x direction. And this is a very, very, very powerful tool for physics, because anyone that's taken physics, you know that you have like a box, and there's a person pushing on it this way, and there's maybe friction going this way, and for some reason someone else is pushing on it this way. Finding every single vector, and then making your own axes for every single one, and then finding a way for all the axes to interact with each other is incredibly hectic, but that simplifies everything. And then in 3 dimension, this is even more intricate, because you could have curved vectors like this, and you could want something that's orthogonal to every single one of these at every moment. And the way that you do that is because this is in 3 dimension. Have something that sticks out of the board. So you can define every single corner here by this 90-degree vector. So if you see right here, there's a 90 degree right there, 90 degree right there, 90 degrees right there, 90 degrees right there, 90 degrees right there. So this board, every vector that's possible on this board can be defined by this orthogonal vector, which defines the whole thing. And the reason 90 degrees is also special is because they give way to something known as cosine and sine. So the way that this was first derived was that there's a circle with a radius r, and for this case it will be 1. And there's some angle right here, we'll call it theta, because everyone calls it theta. And basically they say that this component is your x, and this component is your y. And the way you find your x is cosine, and the way you find your y is sine. Sine. And everyone knows the theory, cosine squared plus sine squared is equal to 1 squared, or just 1. But basically this gives way to the distance theory, not distance, diagram theorem, just calculate distance. So when someone travels like this, the shortest route made by the 90-degree angle, the hypotenuse, comes from this right here. And for those of you that don't know, the total circumference is 2 pi. And I personally don't like this concept. I really don't like it because how much is half of a circle in pi? Half of a circle is pi. So that right there is pi. When you're first learning this concept and you're learning the idea that half is pi, it's really confusing. And it's not pi's fault, because pi is diameter to circumference. Multiply the diameter by pi, you get the circumference. If you divide circumference by pi, you get the diameter. So pi is 4 diameters. Physics and everything works off of radians. Cosine, sine, everything works off of radians. Radians. When you're trying to calculate the volume of the sphere, they always give you the radius. They will never, ever, I mean they might, just to mess with you. But they will always give you the radius for everything. Your hemisphere, it's always the radius. Everything's radius. So it would be a lot cleaner if there was a variable that we had that was circumference to radius, which we do, and even engineers and math teachers don't know about this. It's known as tau. And it really does make everything so much simpler and smoother. Because if you want half, you're at tau over 2. So instead of being pi, tau over 2. If you want, I don't know, like 5/8, tau 5 over 8. Instead of converting pi into 10/8 or 5/4, which is just a big hassle, throws everyone off, and really confuses everyone. Yeah. Tau is just a lot smoother and cleaner. And doesn't mess with any of your identities. So cosine squared of theta still be equal to 1 plus 2 cosine theta, cosine 2 theta, all over 2. And then there's an identity called Euler's identity. For those of you that are curious. Cosine theta. So you don't forget tau. This is what's known as Euler's identity, that ei to the pi gives you I. Confusing, right? So what it's saying is that there's an imaginary axis and then real axis at pi, or not pi, this is pi. See? It's confusing. So when you're at pi, that's pi, you get -1. So you get, this will go to 0, and this will go to -1. So e to I pi is -1. That comes from Euler's identity. But if you substitute tau in there, e I to the tau, now you're all the way over here. So cosine tau would be 1. This would still be 0. And that's that. Basically, -1 squared is equal to 1. And this all comes from an idea of 90 degrees. Because there's an imaginary component. This is imaginary. And this is real. 90 degree theta. That's the power of 90 degrees. My name's Carlos. Thank you for your time.